So in this video, I want to use multivariable calculus and apply that to find the formula for the least squares approximation in linear regression. So suppose that you have data points. So you're given data points x1, y1 up to xn, yn. So you have your data like this, and the idea is you want to summarize the data using a line, so maybe this line. And what you want to do is, so if your line is y equals mx plus b, what you want to do is you want to look at the differences between the observed yi, so if this is your xi, this value here is the observed yi, but this value is just going to be mxi plus b. And you look at the difference in those values. And you take each of those differences and you square them and add them up. And in least squares approximation, you want to minimize that. So what you want to do is you want to choose m and b that minimize the function, well, it's a function of m and b, and it's y1 minus mx1 plus b squared plus dot 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 plus yn minus mxn plus b squared. Okay, well, this is a function of several variables, right? It's a function of m and b. So what you want to do is you want to find the critical points of this function d. So we take the partial derivative with respect to m. Well, before we take the partial derivative, it might help to expand this. And when you expand this, so this is the sum from I equals 1 to n of yi minus mxi plus b squared. If you distribute it all out, you will get the sum of the yi squared minus, and then you're going to get a 2m times the sum of I equals 1 to n of xiyi minus 2b times the sum of the yi from I equals 1 to n plus the sum from I equals 1 to n of mxi plus b squared. Okay. If you don't see how this works, I mean, just expand it out, and then you have this difference, right? Like this yi minus some expression and then squared, and then when you distribute it all out, it turns out that this is what you get. So let's just assume that this is correct. And okay, I'm not going to go over this because it's just algebra. So now we can take the partial derivative with respect to m. And so this first term, the sum of the yi squared, will not show up. You're going to get negative 2 times the sum of the xiyi from 1 to n. And then there's something from the last term. You're going to get plus the sum from I equals 1 to n of 2 times mxi plus bxi. Okay, and I'm going to rewrite this as negative 2 times the sum from I equals 1 to n of xi yi plus 2m times the sum of xi squared from I equals 1 to n plus 2b times the sum of the xi from I equals 1 to n. So that's the partial derivative of d with respect to m. Now we need to take the partial derivative with respect to b. And it turns out that you're going to get negative 2 times the sum from I equals 1 to n of yi plus the sum from I equals 1 to n of 2 times mxi plus b. And then that's going to be negative 2 times the sum from I equals 1 to n of yi plus 2m times the sum from I equals 1 to n of xi plus 2nb. So now we set each of these partial derivatives equal to 0. And so that's going to give you, let's see, if you divide by 2 and then move things to the other side, this first equation is going to be the sum of xi squared times m plus the sum of the xi's times b equals the sum of the xi yi. And then the second one turns into the sum of the xi times m times b plus n times b equals the sum of the yi's. So all these sums are from I equals 1 to n. Now you know, it looks complicated, but this is actually like a constant, right? These are all constants. So this is just a system of two linear equations. I can write this in matrix notation as the sum of the xi squared, sum of the xi, sum of the xi n times mb equals sum of the xi yi, sum of the yi's. So this is just like a x equals b, right? And I can multiply by a inverse using the formula for the inverse. And when you do that, you end up getting, so x is equal to a inverse b. And if you just find a inverse using the formula and then plug it in, what you end up getting is m is n times the sum of xi yi minus the sum of the xi times the sum of the yi divided by n times the sum of the xi squared minus the sum of the xi squared, and b is equal to the sum of xi squared times the sum of the yi minus the sum of the xi times the sum of the xi yi divided by n times the sum of the xi squared minus the sum of the xi squared. That's what you end up getting. One thing that we actually should check is that the denominator can't be 0. So in other words, in terms of the matrices, that this matrix A is actually invertible. We should check that n times the sum of the xi squared minus the sum of the xi, and parentheses squared is not 0. This is actually true. It follows from something called the Cauchy-Schwarz inequality. And what the Cauchy-Schwarz inequality says is that if you have, so in terms of vectors, it says that the absolute value of the dot product of two vectors is less than the product of the magnitudes of those vectors. And if you apply that with u equals 1, 1, 1, and v equals x1 through xn, you end up getting that the magnitude of the dot product is, well, the dot product is just the sum of x1 to xn. So then, so it's just the absolute value of this, and then the length of u is just the square root of n, and the length of v is the square root of x1 squared plus dot 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 plus xn squared. So then, when you look at the length of u times the length of v squared, that's going to be n times x1 squared plus dot 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 plus xn squared. And that's what I have here. And then on the other side, if I take the dot product of u and v and square it, then I just get x1 plus dot 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 plus xn in parentheses squared. Oh, and it's important that this is actually an inequality, but this happens with equality if and only if u and v are parallel. And since all the xi's are not assumed to be the same, right, then v is not parallel to u. So this is okay. Right, so the sum of the xi squared is this other term here. So by the Cauchy-Schwarz inequality, they're not equal. And so the denominator is not 0. The other thing we still have to check is actually that that this is actually a minimum. Now I'm going to skip the computation of that and let's just take for granted that you do have a minimum and not a saddle point or a maximum. So now this shows finally that we've used multivariable calculus to calculate these coefficients. Okay, thanks.